But let's do a quick recap. What we talked about is we talked about scalar potential for a function. That means that a scalar function for vector field. So what is a scalar potential? Potential for vector field F. That's a function, a scalar valued function, little f, such that the gradient of little f is equal to the vector function. And so there are stories in there, right? You want the little f to be differentiable, have partial derivatives and continuous partial derivatives and that sort of things. And then a field is a vector field is conservative if it has potential function on a nice connected domain, basically. Now, that said, the next thing that we said is that if a vector field has a scalar potential, it probably has infinitely many scalar potential. It has infinitely many scalar potential, and every two of those are just different by a constant. That resembles that antiderivative, basically antiderivative concept from calculus 1, when we had antiderivatives and they were only different by a constant. So big plus big C was the story. And so that exactly comes out to be something that we're going to have in this course, basically. So open connected domains and conservative gives you sort of an antiderivative sort of a feeling for Calc 3. And then what else did we say? We said, let's say F is conservative vector field, then we sort of showed that curl of, because if it's a conservative vector field, then F is equal to some gradient of some scalar function, right? And then we showed that curl of gradient of F, little f, is going to be a zero vector. Again, it has something to do with F having all sort of derivatives and those derivatives being continuous, right? Because we're going to use the Claris theorem. That said, and so that's the main stories that we discussed, and we ended up with this concept that, okay, so if we have curl of curl of F equal to 0, because see, it says curl of F is equal to 0 if F is conservative. And then we said, well, what if its curl of F is 0? Does that mean F is conservative? That's the story that we tell in section the other way around. So this direction is 16.1. The 16.2 gives you the other direction. And it's not quite the other direction, because you need one more condition plus curl of F equal to 0 vector to have a conservative field. And that condition has to do with the domain of F. So basically, I did a quick review. Now that we know this, what I want to tell you is how to find, what we do for the rest of this section is how to find the potential. In the FQ, you learn a very a systematic way. What I'm going to do for 127, so in 220, Math 220, you learn a systematic way, which is better than the one that I'm teaching you. But our way is quicker for most functions. 220 is quicker for all, 220 is the same pace for the method in there is the same pace for all functions. The method that I teach you in here are quicker for most functions that we use. Is quicker for our functions. So let's learn both of them. And so now let's start with a question like this. Example 3, find the scalar potential function for a vector field that is that. Okay, so let me see, what is a potential function? Potential, I'm looking for f of x and y. See, there's 2 variables here. This is potential function for functions of 2 variables, right? I'm looking for f of x and y such that gradient of f is equal to f, right? That means that the partial of f respect to x is equal to 3 plus 3x, no, 3 plus 2. My bad. 3 plus 2xy, and partial of f respect to y is equal to x squared minus 3y squared. Everybody agrees on that? So your first basically instinct is that, well, why don't you just take the antiderivative? Here it says, see, here the derivative with respect to x gives me this. So antiderivative of that with respect to x should give me the function. And here derivative with respect to y gives me, but let's take the antiderivative, right? So I'm starting from this section. And I'm carrying both of them at the same time. So I get the partial respect to x is the first one. Partial respect to y is the second one. And then so I do the antiderivative of partial respect to x. And then what do I get? And I do antiderivative of partial respect to y separately. Let me finish that one and I come back to here. Okay, so this one, antiderivative with respect to x gives me 3x plus x squared y, right? And then what am I missing? A constant. Let's call it C1. Wait a minute, it's a constant, right? Constant can be a number, but wait, I took the antiderivative with respect to x. There's a variable that can be constant too. What is that variable? Y can be constant, right? So this can be the actual constant we like, and it can be y in there too. And over here, now I take the antiderivative with respect to y, and I get, oh, what am I missing? C2, right? Let's call it C2. Oh, C2 can be numbers, but wait a minute, this was with respect to y. So x is a constant with respect to y also. So I'm putting it there. Now, what you see is, oh, look at this part. That's a common thing between the two of them. But look, what do I do with this? That's not over there. They're supposed to be the same thing. They're both supposed to be f, right? Both of these are supposed to be f of x and y, because I took the antiderivative of same thing. So both of those are supposed to be antiderivative of same thing, but they're the components that are not the same. Oh my. But here's the deal. Look at this. This is just function. Is this function of y only? So that was the constant that showed up in that antiderivative. And over here, is this a function of x only? So that was the constant that showed up in that antiderivative. So you really have them on both. You just don't know what this C2 is. That tells me that C2 is 3x. This one tells me that C1 is minus y to the third over. Why do I have over 2? And why didn't you guys yell at me for that? There we go. So that was the story. I could not take. You did not see that I cannot take antiderivative of polynomials, so that's okay. But now, so what do I do? So I'm thinking basically f of x and y is that 3x. Is that 3x plus x squared y plus minus y to the third. So the common one I wrote once, and I figured out the ones that are acting like constant in other places, but they show up in one place, I write them once too. 3x is only showing up in one, minus y squared is showing in one, and x squared y shows up in both of them, and this becomes the scalar potential. So I took the antiderivative component-wise, compared, so take antiderivative component-wise. Yes.
So why do you have to add that constant c for the function of xy if you already know when you take the antiderivative?
Yeah, so the part is that I said, look, the black arrow goes from negative y to the third to c1 of y, right?
Yeah, which makes sense. So you'd include that in the function. Okay.
So this c1 of y could have been negative y to the third plus 5. So that 5 doesn't show in any of them. So that's the story that we had in the iClicker, that you can't have all these numbers that I don't know, right?
Okay, yes.
So that, again, it's just like the taking the antiderivative. And
thank you, Jill.
One, no problem. And so that take the antiderivative component-wise, mind your constants every time with respect to the components variable. Sorry, that is a long thing that I missed. Components variable. That's like first component in respect to x, second component in respect to y, and mind your constants to be function of the other variables. Functions of the other variable. I started clean and I messed up. And then 2, compare and find the scalar potential. So that was the method that we did basically. We took the antiderivative, each component respect to the variable that matches that component. Now, what if I have the functions of 3 variables? So again, I'm looking for the scalar potential. So I'm looking for f of x and y and z, the little f of x and y and z, such that the gradient of f is going to be equal to the big F, right? So, and again, I know that that means that this means that the partial of f, little f respect to x is equal to the first component of f, partial of f respect to y is equal to second component of f, partial of f respect to z is equal to the third component of f. And so what you do is you, to find the f, you take the antiderivatives. This one, you take the antiderivative of y squared plus e to the z dx. That one, you take the antiderivative of 2xy plus secant square of y dy. And the third one, in x e to the z dz. Right? So what is going to happen? For the first one, I will get xy squared plus x times e to the z plus constant c1 of, what are the variables that are constant with respect to x? Y and z. Then for that one, I get x y squared plus What's the antiderivative of secant square of y? That's tan of y, right? So, and then plus, what are the variables that are constant with respect to y, x, and z? And then for the last one, you get x is a constant coefficient, e to the z, the antiderivative of that, just e to the z. Then plus, what is the constant in terms, it would be x and y. Now, what are the common terms in here? And I made it too big, I think. There we go. So what are the constant terms? Let's see. The constant terms are these two. I'm sorry, common terms are these two. And they don't show up in the last piece, right? Look at this. This one, you don't see them explicitly in the last piece. But wait a minute, x, y squared, is that a function of x and y? Yeah. So this is okay. And this is okay. So I can start writing this out. I can write f of x and y. This xy squared is showing up everywhere, xy squared. And then let's look at the other things that are showing up. There's one more common item. What is that? These two are showing up in two of these, x e to the z, x e to the z. But wait, C2 in here, they don't show up explicitly, but if the constant in here is a function of x and z. So I'm gonna write, I should have written it in the nice coloring there until I kind of back myself out. Now, what is the last thing that is showing up? The last thing that is showing up is tangent of y. Last term that is showing up and it's not in common in any of them. But here's the thing. Tangent of y can be a constant in here and also be a constant, different color, in there. So that's okay too. It just didn't show up, the term didn't show up in here or here, it showed up as a constant. So I'm writing it tan of y plus c. And so this is the scalar potential. Do you guys know how to find, to figure out if you found the right scalar potential? Take the gradient of it. It's like, how do you check your antiderivative? You take the derivative of it, right? So if I take the gradient of f, I should get the big F. If you want to check,